Hi, my name is Mia Bashara, and today we're going to be going through Physics 2, Lab 2, all about magnets. So let's go ahead and get started. Why are we doing this lab? Number one, we want to observe real-life magnetic fields through a visual representation while understanding the relationships between distance and magnetic field. We want to analyze concepts of magnetic fields using the fundamental principles such as the Bouts-of-Arc law, and develop our glow skip coding skills, woohoo, by creating a computational model to communicate real-world observations. Most of all, we're modeling a magnetic dipole using a bar magnet. And the main results of this is I found mu to equal 2.208 amps meters squared, and n, which we'll discuss later, is negative 3.04. And what we really found is real-world experiment is a fairly accurate model for analyzing the magnetic field, this experiment in general. So the fundamental principles that we really need to know is really the Bouts-of-Arc law. We know that electric current produces a magnetic field, as we've learned through the lectures, and a moving charge actually is the thing that produces the magnetic field. This is the distance dependent. These two right here are the distance dependent formulas of the magnetic field. This is K, which is a constant, R, the distance, the N, and this is the linearized format of this to make sure that we can graph it. And over here is a more accurate representation of the Bouts-of-Arc law rather than the one that we found in class using dot products and all that. So the key assumptions that we're taking is that the bar magnet is a magnetic dipole, and we did this to properly apply the Bouts-of-Arc law. And so just to get into the experiment, the procedure, etc., the system was defined as the bar magnet, with the surroundings being the earth and really everything else. The initial conditions were defined by the bar magnet and the magnometer on the phone. And what we found is that we as in me, like the location of the magnometer on a phone, like to do this procedure, we located the location of the magnometer on the phone, pinpointed by sliding the phone horizontally and vertically perpendicular to the ruler. And we made sure that the bar magnet, this little gray block, was on one end to ensure that we were recording the correct position of the strongest magnetic field. The on-axis distance from the magnetic field to the magnometer was found using the ruler for different magnetic fields, and the values were then linearized and put on a graph. So this is really just the overall view of the data or the data that we found. And this is the chart that communicates everything. Y equals mx plus b, or in this case, minus b. And this is the equation that we saw right here, where y is this. This is the x-intercept k, n is being the slope, and ln of r is the x value, I guess. And for the second part of the experiment, we found that the off-axis magnetic field of the bar using the procedures as described in the lab protocol. And basically, we found out that the d-perp in as averaged out was 0.165, which I inputted into the code. And we corrected for the different components, the XYZ components of the magnetic field because of the magnetic field of the Earth. So as you can see here that the Y component that we measured was much higher than the corrected version. And this is because we're taking into account the magnetic field of the Earth. And so to calculate mu, basically I set the two equations that we discussed earlier equal to each other and plugged in K and N using the formula from the graph that we found. And so N being the slope, negative 3.0411, and ln of K, negative 14.633, which we found out K to be 4.42 e to the negative 7. And that's what we got our mu 2.208 amps meter squared. So to the code, what initially we did was create a cylinder that put a position that basically created the magnet to model it in the code. I inputted the mu that I found in the last slide right here, 2.208. And this function right here basically defines any a magnetic field at any position relative to the magnet that we found here. And then we made 6 observations locations, 2 on axis, 4 perpendicular to the axis. And as you can see here, this and on the next slide, we basically defined those points and found the magnitude and direction of each of the magnetic fields there. I plugged in here to find the magnetic field 45 degrees off axis, this little magenta arrow right here. I basically use the position d perp as defined in the experiment, the first part of the experiment, 0.165, and found plotted it as an arrow and defined it and using the function that I created earlier right here. And so, just to compare and contrast, the theoretical off-axis value was 2.75, and the measured one was 6.38, which resulted in a 56.9% error. Really is not that much of a difference compared to the code in real world, so we're grateful for that. The first and the fourth observations were the ones that I observed, so measured a near zero magnetic field at the x direction, and these are the sources of error. The location of the magnetometer on the phone or incorrect magnetic field of the Earth. And so for the first what if question, it would basically yield a much less accurate result, and the Earth's magnetic field would interfered with the recordings and skew the results. And for the second what if, we would have gotten the same direction but different magnitudes, which leads to a different dipole moment. Thank you so much.